variation of conductivity and molar conductivity with concentration. Now, conductivity. Conductivity decreases with decrease in concentration because conductivity is per unit volume on dilution concentration decrease, that is number of ions that carries current decreases per unit volume. Therefore, conductivity decrease with the decrease in concentration. This is very important for board level and competitive exam level. Reason. Now, for example, this is 1 unit volume. This is 1 unit volume. So this is an electrode. This is an electrode. Whatever the inside electrolyte is present, that is completely 1 unit volume. That 1 unit volume nothing but 1 centimeter cube or 1 meter cube. Now I am adding water. If you add water, then what will happen? All these liquid flow out. When flow out, along this some electrolyte also comes out. It meaning number of ions, for example NaCl, that NaCl also flow out. Therefore, number of ion carries current decreases. Next, molar conductivity. Molar conductivity increases with decrease in concentration. For strong electrolyte and also for weak electrolyte. Strong electrolyte on dilution already they are completely ionized. If anything small amount left, that also completely ionized on dilution. And one more thing, force of attraction decreases. When force of attraction decreases, their movement increases. Therefore, lambda m molar conductivity increases. For weak electrolyte, what will happen? On dilution, degree of ionization increases. When degree of ionization increases, number of ions increase. Therefore, molar conductivity increases. Simply you have to remember molar conductivity increases on dilution. On dilution means decrease in concentration. This is represented the variation of lambda m molar conductivity with lambda m with concentration for strong electrolyte and weak electrolyte is different. Both increases, but it is different. First of all, we should know that K. K meaning what is the conductivity of 1 unit volume. Carefully note down 1 unit volume respective this is. Lambda m mean what is that? Here L is constant 1 unit, but area is not constant. Area may be variable. This is called given volume. Volume is very not very high, not very small. Next, lambda naught m. Lambda naught m meaning what is that? Same. L is equal to 1 unit. Area is variable, but this variable is large sufficient, very large. Therefore, this is called at infinite dilution. At infinite dilution meaning that is called zero concentration. So, this lambda m or lambda naught m, anything, these are variable with concentration. Now, for strong electrolyte and weak electrolyte is different. So, what is the lambda naught m? Lambda naught m is called limiting molar conductivity. What is the limiting molar conductivity definition? Now, the conductance of a electrolyte kept between electrodes of a conductivity cell 1 unit distance and having area of cross section large enough to accommodate sufficient volume that contain 1 mole of electrolyte when concentration approaches to 0. That is called limiting molar conductivity. Now, same explanation as like molar conductivity. This is 1 cube. In this, we have this distance is between the two electrode is 1 meter, that is fixed. Now, whatever these are the electrodes, left side, right side. Area is not fixed. This length, this length is not fixed. Sufficient area. This length and this length is not fixed. Therefore, what happened? Volume between these two electrode, how much meaning is sufficient, as much we can add the water that can accommodate. That is called limiting molar conductivity. Now, this limiting molar conductivity for strong electrolyte, weak electrolyte variation is different. This can be for strong electrolyte. Now we can discuss for strong electrolyte. Variation of molar conductivity for strong electrolyte. Lambda m for strong electrolyte. This can be studied based on what you call Debye-Hückel Ansager equation. What is the Debye-Hückel Ansager equation? Lambda m is equal to lambda naught m minus a root c. This is called Debye-Hückel Ansager equation. In this, lambda m meaning what is that? Molar conductivity. Lambda naught m is called limiting molar conductivity. Next, A is constant, C is concentration. Now, this can be explained by using a graph. On x-axis taken root c, on y-axis taken lambda m. Now, according to this formula, lambda m is equal to lambda naught m minus a root c. So, first of all, this is like this for strong electrolyte. Example KCl. For strong electrolyte, initially at this point, it means at higher concentration. Then concentration decreases on dilution. Concentration decrease on dilution. Concentration decrease on dilution, but limiting molar conductivity slightly increases. You observe here, this is the initial point and this is the final. In molar conductivity, little increased in molar conductivity. Reason, force of attraction decreases, otherwise little degree of ionization increases. Actually it is completely ionized, but also anything small amount left, that also ionized, therefore a little increase. Now, how to get this limiting molar conductivity? Extrapolation of this line, then you will get like this. At this point, this is called lambda naught m, that is called intercept. So, extrapolation of the line, we can get the lambda naught m. This is for strong electrolyte. Yes, a strong electrolyte. Now I am taking one weak electrolyte, that is acetic acid, CH3COOH, weak electrolyte, weak acid. So now this graph is different than the strong electrolyte, like this, like this. Now if you consider this one, this is at high concentration. On dilution, concentration decrease, but this molar content nearly same is there. But at this concentration, suddenly degree of ionization increase, therefore number of ion at a time increase, therefore this graph suddenly rise and parallel to the y-axis. So we cannot extrapolation this graph because this is parallel to which one? Y-axis. That's why we cannot get the lambda naught m. So lambda naught m obtain for strong electrolyte by using this formula. Lambda m is equal to lambda naught m minus A root C, but for not for weak electrolyte. Now A is constant, that is now slope, minus A is a slope. Therefore this is different for different type of electrolyte, that is 1:1 all electrolyte same A value. 1:2 type all electrolyte same A value. Similarly, 2 is to all 2:2 type all electrolyte same A value. So A value depends on type of electrolytes. Now we know that lambda naught m for strong electrolyte can be determined by using Debye-Hückel-Ansager equation. Lambda naught m can be determined by using Debye-Hückel-Ansager equation. Lambda m is equal to lambda naught m minus A root C for strong electrolyte, not for weak electrolyte. This can be determined by using Kohlrausch law. Lambda naught m for weak electrolyte can be determined by using Kohlrausch law. Before that, how we can determine? Kohlrausch is observed some similarities in some compounds, that is lambda m KCl minus lambda naught m, that is NaCl, is equal to lambda naught m KBr minus lambda naught m NaBr, is equal to lambda naught m Ki is minus lambda naught m NaI, that equal to 23.4 Simon centimeter square mole inverse. How this value is determined mean? For example, I will take this one component, lambda naught m KCl ionized into K plus lambda naught m Cl minus symbol of this one, and lambda naught m Na plus minus, again this minus applicable here, lambda naught m Cl minus. Now this plus Cl minus Cl minus cancel. What is left? K plus and Na plus. These values are already known from Debye-Hackl-Ansager equation. By adding, these values are given in the table. So both value add, then we will get, not adding here, this value subtract everything. Lambda naught m k plus minus lambda naught m na plus. Write the k plus value and na plus value, then we'll get this difference is a 23.4 Simon centimeter square mole inverse. Similarly, lambda naught m na br minus lambda naught m na cl is equal to lambda naught m kbr minus lambda naught m kcl is equal to 1.8 Simon centimeter square mole inverse. So that is nothing but, if I take this one, ionize into lambda m na plus lambda naught m br minus symbol of minus, this one, lambda naught m na plus minus symbol required minus lambda naught m cl minus. What happened now? This Na plus cancel. Then what is left now? Lambda naught m br minus lambda naught m cl minus. These value difference is 1.8 Simon centimeter square mole inverse. Next, what is the Kohlrausch law? This is very important for board level and also for competitive exams. What is a Kohlrausch law? I will take one example of any one electrolyte. For example, NaCl ionize into Na plus Cl minus. Its limiting molar conductivity is lambda naught m NaCl is equal to lambda naught m Na plus lambda naught m Cl minus. One cation, that's why one cation, one anion, that's why one anion. Okay, so this is the limiting molar conductivity. Limiting molar conductivity of an electrolyte is equal to limiting molar conductivity of cation and limiting molar conductivity of anion. So what is the definition now? According to this formula, limiting molar conductivity of an electrolyte is sum of limiting molar conductivity of cation and anion. That is called Kohlrausch law. This is the definition for Kohlrausch law. Now, I am taking one general example. X moles of AXBY ionize into X moles of AY plus Y moles of BX minus. Therefore, limiting molar conductivity of AX By is equal to X moles of limiting molar conductivity of A Y plus Y moles of limiting molar conductivity of B X minus. This is a in general formula, but in textbook it is given as limiting molar conductivity of an electrolyte is equal to mu plus lambda naught m cation plus mu minus lambda naught m anion. If mu plus mu minus mean number of cation, either number of anion. So here already we can easily identify according to this formula how much here number, that number will be there. How much number here, that number. So number of cation and number of anion. So this is about the um, limiting molar conductivity of any electrolyte. So already I told you that limiting molar conductivity of weak electrolytes can be calculated or determined by Kohlrausch law. Now that I am utilizing example, acetic acid. Acetic acid is a weak electrolyte. It ionizes into CH3, COO minus plus H plus. Lambda naught M for acetic acid is equal to 1 anion. Therefore, lambda naught M CH3 COO minus plus 1 cation lambda naught M H plus. Then these ions are also belongs to strong electrolyte. This ion value we can get from the strong electrolyte by using Debye-Huckel-Ansager equation. Carefully remember that these are also one of the anion and cation for the strong electrolyte. How this is determined mean example, lambda naught M acetic acid is equal to lambda naught M CH3COO Na sodium acetate plus lambda naught M HCl minus lambda naught M NaCl. How we know this is reason? In this we have one CH3COO minus, another we have H. So in any one of the strong electrode we have, that is CH3COO minus, and another strong electrode should have H plus. Remaining these ions may be any other, may be sodium or potassium. This may be any other Br minus or I minus also. Then these are compulsory, next part will be in the minus. Then these are cancel out. How these are cancel out? See, now lambda naught M, this sodium acetate ionize into CH3 COO minus plus lambda naught M Na plus this plus and lambda naught M H plus lambda naught M Cl minus. This minus lambda naught M Na minus lambda naught M Cl minus. Now what will happen? This positive Na plus and negative Na plus cancel out. Positive Cl minus, negative Cl minus cancel out. So what is left now? This is and this is. These both are which one? one acetate ion, one H plus ion. These are equal to which one? Acetic acid. Therefore, now I will take one more example, then you can easily understand. Now, example is lambda naught M barium sulfate. Lambda naught M barium sulfate. Now, this is a one weak electrolyte. Consider. Then, how we can write lambda naught M barium plus 2 plus lambda naught M SO4 minus 2, because barium sulfate ionize into barium plus ion, barium plus 2 ion plus SO4 minus 2 ion. Now keep in mind how to write this is lambda naught M barium sulfate is equal to lambda naught M barium ion should present, barium, and plus lambda naught M SO4 should be present, SO4, that equal to lambda naught M. Now here whatever ion is it, that both combination should be here. Now I am taking here Cl to barium chloride, and at this place I am taking the H plus, it means H2SO4. Then what should be required here? Here H and Cl, that is HCl. But how many chlorines are there? How many hydrogens are there? 2 times is there. That's why don't write here 2. That should be here 2. Here minus. Okay. Now you check that 2 chlorines cancel with respect to this one. 2 hydrogen and these 2 hydrogens are cancelled out. What is left? Barium and sulfate ion is left. That's why this is equal to this one. Anything given like this, you can easily write. Example, lambda naught M NH4OH is equal to lambda naught M NH4 plus lambda naught M and OH minus. Now this is equal to which one? Lambda naught M NH4 OH is equal to lambda naught M. First you write NH4, another one lambda naught M OH minus we want minus lambda naught M. So whatever the ions here comes, that will be written here. Now I am taking example here chlorine, and I am taking here sodium, or you can take potassium also, no problem. Then what we can write here? NaCl, because this Na will cancel after ionization. This Cl will cancel after ionization. Then what will be left? Ammonium ion, this will be equal to this one, and OH minus ion, this equal to this one. Therefore, like this will be calculated limiting molar conductivity of weak electrolytes. Degree of ionization or dissociation. So this will be calculated by using formula alpha is equal to lambda m by lambda naught m. How this is calculated? Meaning alpha value is equal to 1 at lambda naught m, at infinite dilution completely ionized. Okay, then at lambda m, then how much this value, then whatever that opposite to the question mark, that should be denominator. Therefore alpha is equal to lambda naught m into lambda m. This is called degree of ionization formula. Next, dissociation constant of weak electrolyte Example, Ka for acid, Kb for base, K general, anything that is acid, base or any other purpose we can write K. So this also we can calculate by using Kohlrausch law. Example, Ka, how to calculate? Example is acetic acid. This will be ionized into CH3, COO minus plus H plus. T equal to 0 times C concentration dash dash. T equal to T time equilibrium time. C minus C alpha, C alpha, C alpha. Now Ka, acid dissociation constant. Acid dissociation constant. This can be written as Ka is equal to H plus N concentration into CH3COO minus N concentration, denominator CH3COOH concentration. These numerator concentrations are, one is C alpha and C alpha. Denominator C taken common 1 minus alpha, therefore C into 1 minus alpha. C cancel, therefore C alpha into alpha, alpha square. Denominator 1 minus alpha, that is equal to Ka. If alpha is less than 1, then 1 minus alpha is equal to 1. When we can say this less than 1, alpha value is or less than, equal or less than 5%. Otherwise, in that alpha is less than or equal to 0.05. So that time we can say alpha is less than 1, that equal to 1 minus alpha is equal to 1. That is Ka is equal to C alpha square, then 1 minus alpha is equal to 1. That's why Ka is equal to C alpha square. Ka for acetic acid generally known from the first year, that equal to 1.78 into 10 power minus 5, and Kb for NH4OH, that also 1.75 into 10 power minus 5. Then what are the application of Kohlrausch law? Application 1. Lambda naught M for weak electrolyte we can calculate. Second one, alpha we can calculate. Third one, dissociation constant K, meaning Ka or Kb will be calculated. And also when Ka known, pKa also we can calculate, or pKb also we can calculate.